Hello, everyone, and thank you for taking some time out of your day to listen to me talk about network and automation telemetry at scale with the Elastic Stack. My name is Jonathan Dowdy, and I founded Mentat about 7 years ago with the vision to make automation simple, secure, and scalable. And one of the core tool chains that we use on a day-to-day basis is the Elastic Stack itself to sort of help drive that vision forward. Whether it's Elasticsearch to search and store data, or Logstash to parse or Beats to push data, the point is we've tied a lot of our automation around it. And over the past few years, we've developed some automation patterns that help clients scale out and solve different problems. So today I'm going to be talking about one of our larger public sector clients, state and local government, that use one of our automation patterns to help scale out and identify a very particular problem. Unfortunately, due to legal reasons, I'm not able to divulge the name, but you can probably guess who they might be, considering the scale and scope of the problem. So the client has multiple physical data centers spread out across the tri-state area. They have tens of thousands of endpoints producing sort of oceans of data on a daily basis, and they have millions of people that depend on the services that they provide, whether they know it or not. When I say services, think, did your garbage get picked up today, or you dial a particular phone number for help or information? Those services were going offline frequently. For years, they had been fighting fires, fire after fire, and there are different types of fires, right? There's latency issues between endpoints or complete outages of services. The point was they were spending most of their time putting out these fires instead of actually providing better service. So their problem was they didn't have any visibility or any effective or efficient mechanism by which they could see what might be causing all of these fires, right? Because if the fires are randomized, one day there's network latency, another day a whole service is down, there's nowhere you can pinpoint to say that this is the root cause of the problem. So they needed some help identifying what might actually be at that root cause. So that's where we come in a little bit. We met with the clients and asked them the normal set of questions that we would to try to size out an Elasticsearch cluster. What's the velocity of data? How fast is this coming in? How much are we going to have to hold? How much are we going to have to process? Are we going to have to clean it up? What are the basics, right? And we were met with, we don't know. We just have petabytes of data, and we know that there's an underlying problem. We just don't know exactly how to get at it and how to identify it and visualize it. So, of course, we implemented Elasticsearch, that's why we're here, to search and store data. We wanted to get as close as we could to a stateless design for Elasticsearch itself. So we wanted to extract some of the normal services that exist within the tool and put them out so that we could scale them out individually. So we picked Kafka as a durable queue. This acted as sort of a buffer to protect the crown jewels or the data that we're going to be holding and processing to search. Next, we use Kibana to visualize. Pretty easy choice. Next one's a little bit tricky. So we used Ansible, and you can just think in your mind for a moment, and I'll touch on this later. We used Ansible as a replacement in this case for Beats, and it came from a very interesting client requirement that ended up being a very smart, strategic decision. Next, we used Azure DevOps to orchestrate all of our automation. Azure DevOps was a natural choice for us because, interestingly enough, we had built them a separate automation platform to do build and configuration across virtual machines and all the different clouds and on-prem services. So we didn't need much time or effort to integrate Ansible into our automation platform, and we used Azure DevOps to do that. Lastly, we were able to spend some time with the client and identify their root causes of their problems over time. And the outcome, which I'll get to the actual numbers at the end, was a drastic reduction in outages after identifying the root causes. So now the fun stuff, onto the tech part. So on the screen, I've got two different diagrams here. We've got to your left CRCs, which I'll talk about in a little bit of detail. I don't want to overwhelm you. If you're interested in learning more about what CRCs are, aside from my simplistic explanation, you can do a quick Google search for Cisco and CRCs, and there's a very good white paper on it. There's 10, 20 pages explaining all the ins and outs of what CRCs are. As you can see, Keanu's quite confused. Next to that, we have the architecture that we use to scale out and approach that sort of stateless design for Elasticsearch which ended up being incredibly important given all of the unknowns. Right? So typically when we go into these situations where we have almost all unknown, right? We just know we have to solve a particular problem, we break things down into a set of layers. So the first thing we wanted to do is identify what might actually be causing the problems, and we wanted to start at the lowest layer within all of their different data centers. So we're talking about physical devices that are transporting data between endpoints, not virtual machines, not applications, because there was no predictable pattern as to what was actually causing the outages. So we identified data emitters, what switches, routers, firewalls, load balancers, storage arrays, a whole slew of other devices. What we were looking for at the end of the day was anything that emitted what's called a CRC error code, or a counter. So once we had all of our data sources identified, we implemented our automation orchestration layer. With Azure DevOps, it was really simple for us. We already had a significant number of pipelines and some pipeline templates, so we made a little bit of code changes to integrate Ansible. If you've used pipelines before, they mean fundamentally different things to different technologists, right? DevOps engineers use pipelines to take something that doesn't exist yet, pass it some variables, and build you out maybe some virtual machines or services in AWS, or maybe even run some sort of configuration on-prem in NSXT. But a data scientist is going to take maybe some dirty data and then clean it up, parse it, ship it to another stage in your pipeline, and process the work. The point is, the idea is the same. We used a pipeline, which is a series of stages, to do the work for us with Ansible. So we wrote an Ansible playbook to go out and collect all of this data, which were CRC counters across these thousands of nodes, and we implemented it with Azure DevOps. Below that, we have our infrastructure orchestration layer. And this was critical to our success because, again, we're trying to approach a stateless Elasticsearch design and implementation, because typically we go into engagements with small teams of highly skilled engineers, and we want to focus their efforts on using the tools as opposed to managing the infrastructure. We don't want them trying to determine how big a virtual machine should be or what the configuration of Elasticsearch should be. So instead, what we do is we create small files called manifests, which are very easy. And we basically tell Kubernetes how Elasticsearch should scale. When you meet certain upper and lower bounds, we're going to scale out. When those are also met going in, you'll scale in. So this worked out quite well for us. And with some other tools, we also had a bunch of automation in place that enabled us to not even have to think about outages or if we wanted to spin up even another cluster, because it was polling our Git repositories where we stored all of our infrastructure as code. So we deployed a few Kubernetes clusters on-prem for the client. And then we decided to start working on the services layer, which is going to be implemented inside of the Kubernetes cluster itself. So Kafka was a natural choice for us as well, because we tie a lot of our automation around it, and it meets the needs of what we're trying to do. We wanted to extract the ingestion piece or mechanism that's going to take all the data in for Elasticsearch so that we could have it as a separate service and it would scale out itself. If you haven't used Kafka before, it's pretty simple. It's a durable storage queue, and that's why I'm calling it a buffer. It's basically, we wanted to make sure we capture all that in-flight data until Elasticsearch was ready to have that data written down. And Kafka is quite good at this because it keeps the data for a short period of time and waits for Elasticsearch to be ready. And then when it is ready, it writes the data down to what's called the data stream. So after we implemented Kafka, we took a look at implementing Elasticsearch and then Kibana on top of that. So Kibana was our presentation layer, pretty easy choice. And Elasticsearch was our storage and query layer. The last step before I get to CRCs is we thought, now that we've got the sort of shell, the infrastructure automation, and we also have the automation is going to go out and collect data, transform that data, and then push it down to Elasticsearch, what are some of the basic things that we could do inside of Elasticsearch itself to help us scale that out? So we picked 3 scale metrics, which again, we're trying to approach that stateless architecture. One of them was automated backups to AWS S3. We put that into code so that in the event of a disaster, or if we wanted to spin up n number of clusters, we wouldn't have to think about adding that configuration back. So we had an automated scheduled backup, essentially, of all the indices that would go out every single day. The second scale factor was an aggressive ILM policy. Again, we put the ILM policy into code so that when we wanted to spin up a new one of these clusters, or we had a disaster, it didn't really matter. Kubernetes would handle the infrastructure, And then the code also contained all the configuration we needed in order to scale out Elasticsearch itself. So again, we didn't know how fast the data was going to be coming in. We didn't know how much there was. So the ILM policy we set up was very aggressive. We set up 2 days on a hot tier and then 10 to 14 days, depending on what the client was looking for, on the warm tier. And then after that, we just wanted to get it off, right? I didn't want to think about the backing Ceph storage. I don't want to scale that out too much. And I know I didn't want to hold on to petabytes of data at any given time, especially in Kubernetes. So that was our second scale factor. Again, put that in code. And the third scale factor relates to CRCs specifically. Again, there was so much data that we were looking for one particular metric that we could start with as a foundational layer and then sort of add layers on top of that from a data perspective so we could identify these root causes. And after talking to the client for a while, they said, you know what, there is one thing we can start with, which is going to help us identify potential physical defects on network switches, cards, and even copper and fiber cabling. And that's a CRC. So now I'll get to the confused Keanu. So what is a CRC? A CRC is a cyclical redundancy check. It's a very fancy way of saying two endpoints that want to send a packet between each other are going to run an algorithm. That algorithm spits out a hex code. Now in this example, we have this as an example. That packet wants to be sent between network switch A and switch B. When that packet is about to leave switch A, the CRC check runs and it spits out a hex code. That, for all intents and purposes, it's much more technical than that, but for all intents and purposes, it attaches itself to the packet and sends it across the wire to switch B. Switch B then effectively runs the same exact algorithm and spits out a hex code. So if the hex codes match, then the light is green and the trap is clean. There's nothing you have to do. But if they don't match, then it's red. And you're going to have to increment your CRC counter on your device that's tracking that packet throughout your network. And this is what we were targeting. Because CRCs are incredibly important, like I said, they indicate, not always tell you, but they indicate that you could have bad fiber cables. Maybe somebody bundled them up and compromised the structural integrity, or bad copper. But they could also indicate bad batch of switches, the network card in the switch, or the switch itself. So after a while of putting all this in place, which took about a month or two, we created a really simple Kibana dashboard for the client, because again, we like to keep things pretty simple. So we had a pie chart at the top here, which is just going to give them a simple visual representation of your top offenders. And then the same data represented as a list, but this time you can see a count of the total number of CRCs for a given device. And at the bottom, what ended up being the most helpful for them in the short term during the initial implementation of this was the line chart, which was great for them because at the end of the day, what they were able to do was correlate some of these fires or outages with large upswings in CRC counts across their network. So we started off with this, and we picked a small sample size of 5 nodes. We had 5 nodes that we wanted to connect to and start pulling that data on a routine basis with Azure DevOps and Ansible. And we let it go for about 2 weeks. After about 2 weeks of time, we went back to the client, we showed them the dashboard. They decided to refocus some of their engineering efforts to look at these 5 switches, and what they found was fantastic. 1 of the 5 was physically defective. So they got very excited about this, of course, because if you can imagine managing tens of thousands of endpoints, if 1 out of 5 in your sample size already has a defect, the likelihood that you have more is high. So for us, we had no code changes. We got an immediate approval to expand this across their entire network. All we had to do was take all the host names and IP addresses, add them to a single file, and let the automation go. So with this dashboard, we ended up developing about 20 or 30 of these for them per segment in their network. They found at the end of the day about over 100 devices that were physically defective. So they had to bring in a vendor, come onto site, rip those out of the data center, plug in brand new devices. And as they had done this over the course of 4 to 6 months, their outages or these fires gradually started to decline. Down, 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 down. They started at about 4 outages per day. And an outage could be anything from 5 or 10 minutes, an application blip, to a multi-day initiative with 10 or 15 people on the phone. So they went from 4 a day down to where they're at now, which is about 1 per quarter. And that's a pretty astonishing achievement for them because they have been doing this for years, putting out fires. And now they could transform their engineering team from a reactionary one where they're waiting for fires to occur so that they can go put them out, to a proactive one where they can use really simple dashboards with one simple metric that we're going to eventually layer more metrics on top of, so that they can then target their efforts on fixing problems within their network. The next one that they had us create, which is the last one for the CRCs, was a incredibly simple dashboard as well, because the executives wanted to see how many CRCs are happening within a specific segment of my network. Right? All the other dashboards you saw before, those are simply just for engineers. They want to see below that there was actually the raw data. They can drill in and pick a switch, and they can actually see the information coming off of those devices themselves. This one the executives used to target different segments of their environment, and they can say, well, the server farm has 30,000 in a particular, at any given time. Let's target some of our engineering efforts on looking at why that is the case. Now, as I said before, the CRCs are not inherently going to tell you that you have a network physical defect, because there's always sort of a low-level rumbling of CRCs that will happen on any given day. But they will tell you with two types, rapidly incrementing CRCs or large amounts of CRCs within a collection of devices. So these two dashboards and then the 20 accompanying ones that we built for them ended up saving them a significant amount of time and then helping them transform sort of their organization at the end of the day from reaction to a proactive team. So this is the last one I'll talk about. The success of it was so great, we thought, why not implement something similar for our automation platform that we had implemented for them, which was Terraform to run lots of builds and Ansible to do configurations and a few other little things we threw in there with pipelines. We implemented the same exact pattern to ingest, terabytes and hundreds of terabytes of data across tens of thousands of builds or hundreds of thousands of builds, and created some really simplistic dashboards that help us identify some inefficiencies in our code and then some inefficiencies in some vendors' code to increase overall customer satisfaction. As you can see here, it's pretty simple. What stage of a pipeline ran, what's the average success rate, who's running the pipelines, who's not running the pipelines, which projects have the highest rates. So this gives us the ability to target those pipelines and those teams and help them out. And that is just about it. I think I went a little faster than I expected. I'll talk about what we're doing next. So the success of the CRC project was so great that we're going to be taking that to the next step with Elasticsearch triggers. We're going to be, right now, we've implemented one use case for the client where you basically just create a simple query that's going to look for your conditions. Once those conditions are met, you can do any arbitrary number of tasks. I can send an email, I can hit a web API, I can hit a webhook. So we've implemented this in one use case separate from CRCs for the client, and it's worked out quite well. What happens is we look for a particular condition inside of Azure across about 100 different subscriptions, and when those conditions are met, we just fire off an Ansible playbook to go execute some code that's going to resolve or remediate those issues. We're going to be taking that same thing and moving forward into CRCs, because CRCs not only indicate physical issues within your network, but sometimes can also indicate configuration issues between network switches and devices. And that is it for me. Thank you.